In this tutorial, we are looking at the confusion matrix. It is a straightforward tool that cross-references your guesses with the actual results, so you can see exactly where your model is getting confused. To understand it, we use a basic 2x2 structure. We map the predicted classes against the actual data classes. When a model correctly predicts a positive result, this is a true positive. If it predicts positive but is actually negative, you get a false positive. On the flip side, predicting negative when it is actually positive gives us a false negative. And finally, correctly guessing a negative result is a true negative. From this simple layout, we can extract critical performance metrics. The first and most obvious is accuracy. This is simply the total number of correct predictions divided by all predictions made. It answers a fundamental question. Overall, how often is our model right? While accuracy is great for balanced datasets, it can be deeply misleading if your classes are uneven, which is why we need to look closer. That brings us to precision. Precision focuses purely on your positive predictions. It is calculated by taking your true positives and dividing them by all the positive guesses your models made, including the false ones. In plain terms, when a model claims something is positive, how often is it actually correct? You want high precision when the cost of a false alarm is high, like a spam filter that accidentally blocks an important work email. Next is recall, which is also known as sensitivity. Instead of looking at your guesses, recall looks at the actual data. It divides the true positives by the total number of actual positive cases in your dataset. Let's answer the question, out of all the real positive cases out there, how many did our model successfully catch? High recall is crucial when missing a positive result is dangerous, such as in medical testing where you cannot afford to overlook a disease. Let's look at a practical example to see how this works in the real world. Imagine we are testing a spam filter on a dataset of 100 emails. Out of our 100 emails, our filter flags 50 legitimate spam emails correctly, giving us 50 true positives. However, 10 spam emails slip through the cracks into the main inbox. Those are our 10 false negatives. On the other side, 5 regular emails were mistakenly flagged as spam, resulting in 5 false positives. And finally, 35 clean emails were correctly left alone, giving us 35 true negatives. Now, let's run the math to see how our filter performed. First, we calculate the overall accuracy by adding our correct guesses, 50 plus 35, and dividing by the 100 total emails. This gives us an accuracy of 85%. Next up is precision. We take our 50 true positives and divide them by the total number of emails flagged as spam, which is 50 plus 5. That brings our precision to 91%. That means when our filter says an email is a spam, it is right 91% of the time. Finally, we calculate recall. We divide our 50 true positives by the total number of actual spam emails in a dataset, which is 50 plus 10. That leaves us with a recall of 83%, meaning our filter successfully caught 83% of all the spam emails that were sent. Looking at these numbers, a choice has to be made. Is it worse to let a little spam slide inside the inbox or to accidentally block an important email? Which metrics matter most for a spam filter? Let me know your thoughts in the comments below. Thank you for watching.